Hey guys, how you all doing? It's Jalajor here again, back with another video from Be a Gem at GCSE Chem, and today we're going to be doing section C4.2, Equations and Calculations. So yeah, that's what it's called, and it's a really nice section. I think it's not very hard. It's just basically calculations that are very important. Some of the calculations are very important in chemistry. In your chemistry GCSE, and as I mentioned, this whole of chapter 4 is the calculations chapter, which was one of my favourite chapters in GCSE. Actually, I love the maths part in chemistry, but in chemistry GCSE. But yeah, and again, I'm back in my room to make this video again today because why am I back in my room? Oh yeah, because my family's eating dinner downstairs and watching television, and I've already eaten ate my dinner. Basically, I already ate my dinner, so I've already eaten my dinner. But I don't know how you say it, but you get what I mean. I've already finished my dinner, and so I'm back in my room again. And yesterday I didn't upload. I'm really sorry about that. I needed a break. I felt that I needed a break. And one day was also Independence Day, so happy belated Independence Day to everyone. It was the Indian Independence Day, so obviously on the 14th it was Pakistan Independence Day, and on the 15th it was Indian Independence Day. And on the 15th, yesterday, actually one of the greatest legends actually retired from, two actually legends retired from international cricket, both being from India, is MS Dhoni and Suresh Raina. So MS Dhoni, obviously the bigger legend, but Suresh Raina also a really good guy. Great player, but it was really sad actually to see him retire. See both of them retire really, and they retired. Suresh Raina announced his retirement just minutes after Dhoni announced his, and so Dhoni retired at the age of 39, and Dhoni's retired at the age of 39, and Suresh Raina has retired at the age of 33. So quite a young age he's retired on. He's retired at as Suresh Raina, but it's not a cricket session. This, it's a chemistry session. Just wanted to let you know about that, and it was very sad to hear. But best of luck to him in the future, and for the future. And I got my pen today. I'll be doing some writing on the paper here. And today let's get straight into the video really. I haven't been able to put the links to videos from C3.2 to C4.1. I'll try and put all of them, including C4.2, by the end of today. If not, I'll make sure I do them very soon. I know I keep saying this, I'll make it soon. I keep delaying it, but it's just sometimes I get really busy, and I have mocks next month, so it just doesn't help things. That doesn't I don't have much time, and hopefully that makes sense. Hopefully that's okay, but I'll try and upload them as soon as possible. Put the links to those videos as soon as possible. Now today we're doing C4.2 Equations and Calculations, and it's for higher tier students only, so I'll be putting HT only with the title in the video, basically as in brackets. I'll put that, but and if you're following the student book, it's pages 64 to 65. So again, as I've said, it's C4.2 Equations and Calculations. In the student book, it's pages 64 and 65, so that's the big textbook. And the book I'm using again is the AQA GCSE Chemistry Caboodle Revision Guide. There you go. I should have showed this before, but there you go. So as I mentioned before, we're doing C4.2 Equations and Calculations, and that's what it's called. So straight away we go into worked examples. So let's look at this. So chemical equations. So calculating masses from chemical equations. Now chemical equations show the reactants and products of a reaction. When they are balanced, they show the amount of atoms, molecules, or ions in the reaction. So we've actually gone through balanced equations before. So So for example, here they're showing it. Don't know if you can see it, but here they're showing magnesium. Here they're showing magnesium reacting with oxygen to form magnesium oxide. So there's the equation. 2Mg plus O2 gives 2MgO. So then here it says, so for example, 2 Mg plus O2 gives you 2 MgO, which is magnesium plus oxygen, it gives magnesium oxide. So then here it says, this shows that 2 atoms of magnesium react with 1 molecule of oxygen to form 2 magnesium ions and 2 oxide ions. So hopefully that makes sense, because it's 2 Mg plus O2 gives you 2 MgO. That's what it means, that 2 signifies that there are 2 atoms of magnesium that react with 1 molecule of oxygen. Molecule, we say molecule to everything that's diatomic. So oxygen is a diatomic molecule because it's O2. And so this shows 2 atoms of magnesium reacting with 1 molecule of oxygen to form 2 magnesium ions and 2 oxide ions, because it's 2 MgO. So that's 2 magnesium ions, Mg2 plus. Is magnesium in group 2? Yes, it is. 2 Mg2 plus ions, and then 2. I don't know what I'm looking at, but 2 Mg2 plus ions, and then 2 O2 minus ions, basically 2 oxide ions. So hopefully that makes sense. If we work in moles, the equation tells us that we have 2 moles of atoms, of 2 moles of magnesium atoms reacting with 1 mole of oxygen molecules to produce 2 moles of magnesium oxide. So hopefully that makes sense, because it's just the 2, which is the big number that is in front of all these of all the species in the equations. That's why that's why it's 2 moles of magnesium atoms reacting with 1 mole of oxygen molecules to produce 2 moles of magnesium oxide. So hopefully that makes sense. This means that 48 grams of magnesium react to produce 32 grams of oxygen to give 80 grams of magnesium oxide. So hopefully that makes sense, because the relative atomic mass of magnesium is 24, so 2 times 24 is 48, and the relative atomic mass for oxygen is 16, so 2 times 16, because O2 is 32. So hopefully that makes sense. And 80 grams of magnesium oxide, because it's 2 MgO, so that's 2 times 24 plus 2 times 16, so that's 48 plus 32, which gives you 80. Yeah. So alternatively, if we work out the relative masses from the equation, it's 2 times the AR, which we've been through AR and MR in the last section, but 2 times AR of magnesium plus 2 times AR of oxygen gives 2 times MR of magnesium oxide. The reason why we say MR is because for magnesium oxide is because it's a compound, not a single atom, or not of a single element, basically. So basically, convert this to grams. So we have 80 grams of magnesium oxide, which is the same as when we used in moles. So that's fine. We can convert it into grams, or we could just use the relative atomic mass that is in grams from the periodic table. By the way, you get this. So if we have 5 grams of magnesium, we can work out the mass of magnesium oxide we're going to produce. Because if we have, so let me just see what this is. So let me just see what this is. So if we have 5 grams of magnesium, we can work out the mass of magnesium oxide that we produce using ratios. Because we know that 1 gram of magnesium produces 80 over 48 grams of magnesium oxide, because obviously the magnesium oxide was 80 grams and magnesium is 48. So 1 gram of magnesium oxide, 1 gram of this produces 80 divided by 48, which is, 80 over 48 is... There's 5 over 3, and then we times it by 5, because it was 5 grams of magnesium. That's the ratio, so that's 8.33 grams. And here it says 8.33 grams of MgO. So hopefully that makes sense. I'll show you the working out here afterwards, but if we use the mole calculations, this can be done like this. So 1 mole of magnesium produces 1 mole of magnesium oxide, and 5 grams produce 5 over 24 moles, 5 over 24 moles of magnesium, and so 5 over 24 moles of magnesium oxide. If we use molar ratios, that's how it would work. So then the mass of 5 over 24 mole of MgO equals 5 over 24 times 40 grams, which is 8.33 grams. So hopefully all that makes sense. I'll show you all the working out there. Hopefully you can see all that working out there if I make it closer. And I might not explain it very clearly, but it really is. It's just the molar ratios that you're looking at in this in these calculations. So, for example, because it's 2 MgO, 2 Mg produces 2 MgO, because we looked at that in the balanced equation. That means 5. That means if we have 5 grams of magnesium, That's 5 over 24 moles of magnesium. So that's because 5 over 24, whatever we get, that's the number of moles of magnesium. Because remember, number of moles is the mass over the AR, or the mass over MR. But here it's 5 grams over 24, because that's the molar mass of magnesium. So because it's a 1-to-1 ratio, 5 over 24 means we're going to produce 5 over 24 moles of magnesium oxide as well. And the reason why it's 5 over 24 times 40, it's because magnesium oxide has a relative formula mass of 40. It's 24 plus 16. And it showed 2 ways that we could work it out, really. So you could either use the grams method, or you could use the moles. I'm most likely, most of the time, use the moles method, but you need to be able to do both, really, I think. I don't think it matters which method you use, to be honest with you. You know, at the end of the day, if you get the same answer, it really doesn't matter. You know, you get the same answer from both. So now let's look at questions. So here's a first question of the 2 in the section. The balanced chemical equation for the reaction between calcium and oxygen is this. So 2Ca plus O2 gives you 2CaO. How many moles of calcium atoms react with 1 mole of oxygen molecules? Well, we said 2Ca plus O2 gives you 2CaO. Sorry if the lighting changes in the middle, by the way. Sometimes it goes dark. Sorry about that. But it would be 2 moles of calcium that react with... that would be 2 moles of calcium atoms react with 1 mole of oxygen molecules to produce 2 moles of calcium oxide. So that's the answer should be 2, because it's 2-to-1 ratio. So yeah. So the answer should be 2 there. Yes, it is 2. Yeah, good. Now calculate the mass of calcium oxide that can be produced from 10 grams of calcium carbonate in the reaction this. Now I'll do this one on paper. So this is the reaction. CaCO3 goes to CaO plus CO2 plus CO2. Sorry. So basically, I'm going to use the moles method here. And it says calculate the mass that can be produced from 10 grams of calcium carbonate. So what we're going to do is, this is our reaction. It's calcium carbonate breaking down to give calcium oxide plus carbon dioxide. So we know it says 10 grams of calcium carbonate. So first I'm going to work out the number of moles of calcium carbonate. Well, that's going to be 10 grams over the relative formula mass of calcium carbonate, which is 23, because it's been written here as well. It says AR of calcium is 40, AR of oxygen is 16, and AR of carbon is 12. So that's all we need. If it's calcium carbonate, it's CaCO3. So that's 40 plus 12 plus 16 times 3. I'll show you the working out there as well, which is 10 grams over 100, which is basically 0.1 mole. So hopefully that makes sense. So this is for, again, let me just say CaCO3. So this is for CaCO3. I've done the 10 grams given in the question, the mass over the relative formula mass, which I've shown the calculation here. 40 plus 12 plus 16 times 3, which is 100. So 10 over 100 is 0.1 moles. So that's where you get that from. Then you look at the equation. It says calculate mass of calcium oxide that can be made from 10 grams of calcium carbonate. So 10 grams of calcium carbonate. So we have 0.1 moles of calcium carbonate. So how many moles of calcium oxide we have? Remember, the equation is CaCO3 goes to CaO, which is calcium oxide, plus carbon dioxide, CO2. So how many moles of calcium oxide do we have? It's a 1-to-1 ratio. Therefore, number of moles. Therefore, N is just number of moles of CaO equals 0.01, because it's a 1-to-1 ratio. If it was 2CaO, you just double it. It'd be 0.02. So hopefully that makes sense, because obviously 0.01 is for the calcium carbonate, and if it was calcium carbonate to calcium oxide is 1-to-1, then calcium oxide will also have a number of moles of 0.1. So not 0.01, 0.1, because it's the same molar ratios. If it was 1-to-2, calcium carbonate to calcium oxide, then it would be 0.1 times 2 for calcium oxide, which is obviously 0.2. But here it's 1-to-1 ratio, so it's 0.1. And we want to work out the mass that can be produced. We know that N equals M over Mr. We know that equation. N equals the mass over the molar mass. So we can rearrange that to actually find mass equals N times MR, which is the number of moles times the MR, and the number of moles again we've been through is 0.1 mole of calcium oxide, because that 1-to-1 ratio, because it was CaCO3 goes to CaO plus CO2. All our stoichiometric ratios 1-to-1-to-1. So 0.1 times the relative form mass of calcium oxide. Use the numbers from the periodic table if not given to you. Here they give it to us, so that means that's 40 plus 16. So that's 0.1 times 56, which should give us 5.6 grams. So that means we can produce, so hopefully that makes sense, because it's obviously 0.1 times 5.56, because that is the relative formula mass of calcium oxide, and that is basically 5.6 grams. So from 10 grams of calcium carbonate, we can produce 5.6 grams of calcium oxide. So hopefully that makes sense. I find the moles method much better actually than the other method. I just find that one a bit more confusing. Just use the moles method. I think the moles method makes much more sense. It's just a 1-to-1 ratio or 1-to-2 ratio. Basically, whatever ratio you have to basically multiply or divide by that kind of ratio. So hopefully that makes sense. And the key points, just to finish off, are that balanced. Oh, but by the way, let me just see if I was right. Imagine if I was all wrong. This video would be a disgrace then if I was all wrong. But I believe the answer should be for 5.6 grams. Yes, 10 over 100 times 56, exactly what I did, which is 5.6 grams of CaO, which is calcium oxide. So hopefully that makes sense. Key points are balanced symbol equations tell you the number of moles of substances involved in a chemical reaction. Yep, that's why balanced symbol equations are so important. We went through that in C1.2, why they're so important, because we can do so many calculations with balanced symbol equations and work out how much of a certain product can be produced at how many grams. We've been through that today, and hopefully that makes sense. You can use balanced symbol equations to calculate the masses of reactants and products in a chemical reaction. So yeah, we know that we can use balanced symbol equations to calculate the masses of reactants and products in a chemical equation. We know that, and we just did in that example there. So I hope this video was helpful. That's the end of the section, guys. I'll put HT only because it's a higher tier video only for higher tier students. And make sure to share, like, and subscribe. And if you haven't already, turn the notification bell on so that you're notified and updated when I upload new videos that you can watch. I'll try and put the links to all the sections from C3.2 to now C4.2 up on my website by today. And what else do I have to say? Yeah, the other reason why I was here in my room today was because my laptop needed to be charged as well. But that's the end of the video, guys. The next section is C4.3, which I'll be doing tomorrow, and that is on from masses to balanced equations. So that's what it's called, from masses to balanced equations. So until then, see you guys, and belated happy Independence Day, happy Indian Independence Day, and thank you very much, guys. Bye.